So next we have the derivatives of the trigonometric function. So we're going to look at what's the derivative of sine, cosine, tangent, cosecant, secant, and cotangent. Okay, so just to kind of review, these two limit rules we've seen before. The first one equals 1, the second one equals 0. You'll have more problems on this. These were just on your Chapter 2 tests. They were also on your grade assignment. Okay, and remember, there's variations of this. I could do sine of 4x over x. The limit would be 4. So these are just some of your rules that will come up, okay? Now, they'll look at what's the derivative of sine. Now, hopefully you're already saying you know the derivative of sine is cosine. Okay, remember we did this graphically. I'm not going to do the formal proof to this, but we looked at the graph of sine. So here's the graph of sine in blue. And if I sketch the derivative, just based on our rules, okay, my 4 key points, reference points here, pi over 2 and 3 pi over 2. If I sketch the derivative of this at pi over 2 and 3 pi over 2, the derivative is going to be 0. Okay, from 0 to pi over 2, it's positive. So I'm going to be coming down like this. From pi over 2 to 3 pi over 2, the derivative is negative because the original is going down or decreasing. Okay, and then it's going back up. So if you look, you notice that the derivative of sine's graph is cosine. Okay. What I'm going to do here is I'm just going to give you the derivative. So the derivative of sine is cosine. The derivative of cosine, if we did the same thing, it's negative sine. If you actually took the graph of cosine, graph the derivative, it's actually negative sine, which really is just sine but flipped over your x-axis. Okay, derivative of tangent is secant squared. Now, how would I get that? I could rewrite tangent as sine over cosine, and I could use what rule here? The quotient rule. So I'm telling you it's secant squared, but if we wanted to actually show that, I could write tangent as sine over cosine, and I could use the quotient rule, and it would be equal to secant squared. Okay, the derivative of cosecant is negative cosecant x times cotangent x. Okay, the derivative of secant is secant x times tangent x, and the derivative of cotangent is negative cosecant squared. Okay. Again, if I actually wanted to find the derivative of cosecant, these all come from the derivative of sine and cosine, because you could rewrite cosecant as 1 over sine, and then I could use my quotient rule on that. Same thing for secant, I could write as 1 over cosine, and you could use your quotient rule. Okay. Most important thing is you need to know these 6 derivatives. Okay, they're going to come up. You need to know these 6 things. You filled them in your note sheet. They'll be on the board, on the poster board for a while, but you just need to know your 6 derivatives of your trig functions. Okay, now before we just get to practicing examples, we're just going to look at sine and cosine. And we know that the derivative, so if f of x is sine, the first derivative is cosine. And now if you look to see what's going to end up happening is the derivative of that is negative sine. The derivative of negative sine would be negative cosine. And then the derivative of negative cosine would be sine. And I would just continue to repeat. Okay, so derivative of sine is what? Is cosine. So every 4 it's going to repeat. It's going to be sine, cosine, negative cosine, sine, cosine, negative cosine. Okay, and then the same thing with cosine. If I'm starting with cosine, the derivative of cosine is negative sine. Derivative of negative sine would be negative cosine. The derivative of that would be sine. Derivative of sine would be cosine, and then negative sine again. So why would I ever care to do this or know this? Well, if I said what's the 46th derivative of sine, you would just have to figure out where would 46 fall. Okay, so 1, 2, 3, 4, and then it's just going to keep repeating after that. So, you know, the first, second, third, fourth, fifth derivative is the same thing as first, so it would be here. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, so on and so forth. So 46 would be the same thing as the second derivative. Okay, which would be what? Negative sine. Same thing with cosine. What's the 19th derivative of cosine? Every 4 it's going to repeat. So I'd have 4, 8, 16, then 3 left. So this is really the same thing as the third derivative, which is sine. Okay, so you could find any high derivative of sine or cosine just by using the repeating pattern. Okay, this is just thrown in here. Your Pythagorean trig identities, which we all know the first one easily. The other two come from that. And then your double angle formulas. The only reason you use these is in simplifying my answer. I might use sine squared plus cosine squared to 1, or so on and so forth. Okay, so they're just thrown in here. Again, they're on the board in class, so when we do practice problems, I will refer to them. Okay, all right, so let's do some problems. So now, I want to differentiate x squared times sine. So now, you know, the other rules that we've done so far, which product, quotient, and our power rule, we still use, but now I'm just adding to that. So now when I go to find the derivative of this, I'd have to use the product rule with x squared and sine. So I would have the derivative of x squared, so y prime would equal 2x times the second function, which is sine. Okay, so derivative of the first times second plus the first function times the derivative of the second, which the derivative of sine is cosine. So there's my answer. The only thing I could do is factor out an x. And I'd be left with 2 sine plus x cosine if I factor that x out. Cannot multiply these two together. Remember, cosine of x is one quantity, x is another quantity. Okay, so it's really what we've been doing with the product rule and quotient rule, but now I'm just throwing in the actual trig function, so the derivative of sine, cosine, tangent, and so on. Okay, next example. Differentiate that function, and then for what values of x do I have a horizontal tangent line? So first thing, I need to find the derivative. Okay, how am I going to do that? I'm going to use quotient rule. So I'd have the derivative of the numerator, so derivative of secant first would be secant tangent. So I'd have secant times tangent. Okay, so that's derivative of my numerator, secant tangent, times denominator, 1 plus tangent. Okay, minus secant, the numerator, times the derivative of the denominator, which would be secant squared. Derivative of tangent is secant squared, all over the denominator, 1 plus tangent, the whole thing squared. Okay, now numerator I'm looking at, and I'm going to try to simplify, see what I can take out, and I can actually, if you look at this, I can take out a secant from the two terms. So this is my first term, this is my second term, guys. So if I take a secant out, whoops, I take a secant x out, okay, I'd be left with what? Tangent times 1 plus tangent would be the first term, okay, minus secant squared, all over my denominator, 1 plus tangent squared. Okay, now what else can I do with this? So I have that secant. This turns into tangent plus tan squared, so I'm just going to write that above to save a little room. So distributing, this turns into tangent of x plus tangent squared of x right there, okay, minus secant squared, and then I have the secant out in front, and then I can change, if I go back and I look at my Pythagorean identities to see if I can do anything with the tan squared and secant squared. What does that become? So I have what here? I have tan squared minus secant squared. So tan squared minus secant squared is actually equal to -1. So this would turn into secant of x times tan of x minus 1, all over 1 plus tangent of x squared. So that's why, again, now you can see it in a problem, why I have the Pythagorean identities in there. So just to kind of review a little bit, what did I just do? After I distributed this tangent, I said tan squared minus secant squared right here is equal to -1, so it turned into tangent of x minus 1. Okay, now to finish the problem, I want to know when it has a horizontal tangent. So I'd set this equal to 0. So a horizontal tangent is when the derivative equals 0. So I'd set this equal to 0. And when does a fraction equal 0? So I'd set it equal to 0 when the numerator, so I'd set the numerator equal to 0. So the last step would be, I'd say secant equals 0 and tangent of x minus 1 equals 0. Okay, secant equals 0 and tangent of x minus 1 equals 0, which should give me the values. When does secant equal 0? Never. And this one is saying when does tangent equal 1, which would be pi over 4. Okay, so for what values of x does the graph have a horizontal tangent would be pi over 4. They're my values. Okay, I know seemed a little complicated, but really you're just doing quotient rule, and then we've done this before. Horizontal tangent line just means when the derivative equals 0. Okay, last problem, find the derivative of sine times cosine. So again, I use product rule. Derivative of sine, I would do, is cosine, okay, times the second function, which is cosine, plus the first function, sine, times the derivative of the second, which would be the derivative of cosine is what? Is negative sine. Okay. So now I could simplify. So I have what? Cosine squared minus sine squared. And there's my value. So with these, you do want to multiply out your trig functions, and you want to use your Pythagorean trig identities mainly to simplify your answers when you can. Okay, anytime I can do that, that's what I would want to do. And there's my answer. So this section really isn't anything crazy. It's just using your 6 trig functions in derivative problems.